Okay, guys, welcome back to the fourth video of the segmentation. Today, we'll be discussing geometric sequences. We'll be touching 5 points now, and for this video, I decided to actually do it everything, like do the exercise already, and just trying to explain because the video will take too long if I if we start doing it like recording myself at the same time when I'm doing it, you know? And I think I will do my best to explain what I did. So the 5 points that we will be doing today, it's determine whether or not a sequence is geometric. Find the general term of a geometric sequence. Find the specified terms of a geometric sequence. Find the sums of the first and term of a geometric sequence. Find the sum of an infinity geometric sequences series. Okay, but what happens if we don't have the numbers, if we don't have the sequences? B- But instead, we have in terms of the equation. Let's see that right here we have 1 over 3 n. So obviously we can do here, we can substitute n by the first, by the second, by the third to get all the sequences. But we can do a little trick here as we explain later here with the k plus 1 ak. So a sub k is equal to 1 divided by 3k, and ak plus 1 is 1 divided by 3 to the power of k plus 1. This is to the 3 to the power of k. So we take this same formula, but we replace the a with this right here that it's in parentheses, that it's in brackets. So we have 1 divided by 3 to the power of k divided by 1 divided by 3 to the power of k plus 1. Now, if you don't know how to do this, maybe you're in middle school, or if you know it, the easiest way is to flip 1. So you have 1 divided by 3k. You put the 3 to the power of k, flip it, divided by 1. Multiply by 1 divided by 3k plus 1. It's like saying this number, it's being reversed, multiply it by the whole number. And this will be the same as dividing. I hope I hope you get this. Okay, now you can multiply. And this is very hard to understand because of the powers. So the 1 and 1 we don't really, this can be, we cannot even divide it. Just forget about the ones. Okay? We have 3 to the power of k, and we have 3 to the power of k plus 1. So what I did here, because if you see an exponent that it's being added, we can take the power rules that's saying that kind of like breaking up. So we have 3 to the power of k times 3. Now you may ask where this 3 comes from. Well, this 3 comes from 3 to the power of 1. So 3 to the power 1 times 3 to the power of k. This is equals to this. We just breaking down. Now that we have 3k, we just simply simplify that this is 1 also. So we have 1 because 1 times 1, and then 1 times 3. And 1 divided by 3, it's equals to 3. So the radius, so the whole radius of these sequences of this formula, it's 3. In this example, we will see that it's very important to do this because there are some sequences that are not, like there are some equations that are not, that they don't have a sequence, that they don't have a ratio. So let's consider this. A sub 3. Now, what this a sub 3 means? This a sub 3, we're saying that we will take in the third number of the of the sequence divided by a sub 2. So we can take a sub 4 and a sub 3. We can take any number, but the catch is here. The number on the top has to be like a higher number divided by the lower number. And this is really important because when we look at calculus, the Pythagorean theorem, it's really it's really there. I had to draw it there. I think I show it in the other episodes in which I draw how can we look at this just by looking the graph and in actually looking at it because this is like triangle A. It's like having the difference. But maybe I'm I'm walking away from this. But let's continue. But this is very important. This is a subnotation. Whenever you see a number on the bottom, it's called subnotation. So as we see, the sequence is m squared. Okay. So and the number is 3. So it's 3 to the x, 3 to the square. We're squaring the number, we're squaring the 3. So we have 3 to the third power is 9. 3 to the second power is 4. We have in the ratios. So right here, we have a ratio. So of course, like I said before, we have at least to have 2 or 3 to see if this is really a ratio because you cannot only get one and conclude that this is that this sequences is it has a ratio or not. You had to have at least 2 or confirm or to see that this sequences continues forever and ever with the same ratio. So we take the sixth number. I want to split this up. 6 square, 5 square. If we look at here, this is not the same. Now I want to explain you why. We haven't done anything because we still need to divide this like I did here. This is kind of like 2 because how many 4s can enter in a 9? Probably 2.1 something. How many 25 can enter into 36? 1.6. So as you can see, there's a different ratio here. Okay. In the first term, a sub 1 and the common ratio is r. So we want to come here we want to start building up a formula in which we can conclude that if we put these numbers down here or in the formula that we were about to see, we will always get all the sequences. So we will have the results. So the first term, obviously the first term, it's gonna be the first term. If we take the second term and we divide it by the first term, we get the ratio. So we can write it in this way. The second term would be equal as the first term times the ratio. Now what I'm doing here, I'm taking this, as you can, hopefully you can see my pointer. So what I'm doing is moving this to this side, so we can have, so we can know what's the second sequence. Okay, we're putting it into the second sequences. Okay, let's take a look at the other one, the third term. So if we take the third term, if we divide it by the second term, we always will have the ratio, one ratio. But we still have to take like two ratios, right? But a ratio, it's equals to the first term times the ratio. Okay? Times the ratio. So where did I get this ratio? Well, because the ratio is, it's equals to this, right? So I'm moving this to this side because we are talking about the third term. So this will be a to the first one. So, I mean, sorry, the first sequence times the ratio square. Now let's do the fourth term. We take the fourth term, we divide it by the third term, we have the ratio. We know what the ratio means, right? So the fourth term, it's equals to the third term, because the third term it's equal to a, but the first term times the ratio square. Now a4 means the ratio. So if we want to add this, we just multiply to the ratio. And now we have the one ratio in two ratios here. Well, 2 to the second power, ratio to the second power. If we want to combine this, the only way to combine exponents is by multiplication. So as you can see, we have to make it a multiplication. So we make it to the third power ratio. Wait a minute. So we can take any term. Now the any term means that any number in the sequence. So any number in the sequence divided by a any number minus this minus one means that you cannot take the same number. You have to take another number. Well, you can take the first number. You can take like 7, but we have to make minus 1. So this 7 converts to 6. Now we have a ratio. Okay, now the ratio. don't don't freak out, guys. We're almost there. This ratio means that we have any number in the sequence. Now, any number it's equals to any number, but the other number, the the number behind that number. But we have to multiply it by the ratio. We're doing the same things here. We're taking the ratio because we're taking this number because we're talking about not this number, not 7 or any number, but we're talking about the previous number. So that's what we put here, the previous number. We had to multiply it by pi because because that's the ratio of the first term. Okay, so this means that the first term in the sequence times the ratio to the power of n minus 2. Now, why did we put minus 2? Because if we put, let's say, 7, it will be 5. So we're saying that this ratio it's equals to this number, the 8 minus 1. But we still have to multiply it by the r. So we will get minus 1. So this will be your answer. This will be this will be the equation that will be needed. We just really prove it right here. We can take the first term, but we still have to take, but we still need to know what's the ratio, and then we can take the n. N means any term minus 1. Let's look at this. The formula for the n term of a geometric sequence is a geometric sequence, then the n term has the form. So any number it's equals to the first term times the ratio to the power of 1 minus n. This is really important because if we why 1 minus n? Because if we want to know the first term, guess what? This will be equals to 0. And 0 to the power of r, obviously if we take the first term, 0, any number, if you multiply any number to 0, you will get 1. So 1 times the first sequence, it will be correctly as we said the first term because we just said it, right? The first term is equal to the first term. Now, if we take the second, if we want to know what's the second number in the sequence, so, so we go back. We have to know the first term in the sequence times the ratio. Remember that we took the second number in the ratio. So that number it's the n. So we would take it r to the power of 1 minus 2. So in this case, yes, we take the r. And look at this. Yes, we have to take the r because look at this. This if it took the second square, if it took the second sequence divided by the first sequence, we get the r. So this formula cannot fail. We can take any number and any number that we take, will we get the final answer or any number in the sequence that we wanna know? Let's do three examples. Let's do it fast, okay? Find a specified term of a geometric sequence. We know what's the first term. It's 4. We also know what's the ratio. So this is good. We don't have to take any two numbers to divide it and to get the ratio. But we have to find the eighth term in the sequence. Now take a look at this. We take the eighth term in the sequence. Obviously, we don't know what's the eighth term. We don't know what's the number behind the a. So we just take a sub a. We replace the 8 here. So we will 1 minus 8 will be 7. That's why I wrote 7 here. We take the first term that thank God we know. We know what's the first term. It's 4. So 4 times the ratio minus 1/2 to the power of 7. Now I want you to know how this works. If you have a division and you're multiplying by a power, you have to multiply, you have to give this number into the two division, into the upper and the lower division. Now why I still have 1? Because this 1 will always be 1. But we have a negative 1. We have to be really careful, because if we divide negative, if we power negative by negative, will be positive. But because this number is odd, it will be negative. So it will be always 1. So in this case, this 4, I converted into exponents, and this is really beautiful. You can do this. This minus will give it to the minus 2, 7. So the only thing I did is just subtract this number, like if we're just like if these two numbers wouldn't exist. And this can only happen if we have the same base. That's another rule of exponents. If you guys have the same exponents and you're dividing a multiplication, which is just subtracting the exponents, you can just rightly completely do it. But because the first number, like I said before, the first number is smaller, the number will be smaller, will be minus, will be negative. So we have minus 1 over 2 over 5. And this 2 over 5 will be negative 1 over 32. Let's do it fast. I want to do it fast, but I want to explain everything. Find the seventh term of the following geometric sequences. We have 3, 3/2, 3 divided by 4. We don't know what's the ratio, but we do know what's the first term in the sequence without knowing in what terms are we doing the geometric sequences. Now, what term means? It's really the equation, because we don't know, but we don't really, it doesn't really matter because we know how to take the ratio. Okay, let's continue. We know what's the second. So mm, once you have two numbers in the sequence, you can get the ratio. but we want to know what's the 7. So we want to know what's the ratio and the 7th term in the sequence. We know that the ratio is dividing the second over the first one. So we have 3 divided by 2 divided by 3. So this really doesn't matter. I'm doing it. I did this on purpose because I want to show you that it doesn't matter. You can flip the first fraction or the second fraction. Obviously, this 3, 1 over 3 is not 3 because this 3 should be on top and the 1 should be on the bottom. How many ones can enter in 3? 3. But because I flip it, I had to put 1 here, you know, because I flip it. This number, if this number is 3, now this number doesn't 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 have to be 3. It has to be the double of that. So I just multiply. This is 3. This is 6. 3 times 1, 3. 2 times 3, 6. This is a common. We have a common divider. That it's 2. That I'm sorry. That it's 3. So 1 divided by 1 over 3. I just simplify. Okay. But this is the ratio. So we take the first term. We know what's the first term. It's 3. We take 3 times. Now we want to know what's the 7. I put right here the 7. 7 minus 1 because I changed the n who is in the equation. 7 minus 1, 6. I use the ratio, which it should be 3 because yeah. So we just multiply 1 2 over 6. This is wrong now that I look at it, but it doesn't matter. You will get the concept of how to do this. So like as explained before, it's 1. In this case, if this number would be negative, this will be flipped as a positive and we will get rid of the negative of this fraction. But because this is positive, we don't really see this. 2 over 6 is 64. This should be 3, but doesn't matter. So now, as you can see, we just get rid of the exponent. Now we will do this 3 times this 1 over 64. Now, don't complicate. You can only, you can multiply this 3 to this 1 and you will still have the same answer. This is very famous in electronics when we have the watts, the voltage. It's kind of like a triangle, a magic, a magic triangle in which if you want to know what's this, you can only multiple. I'll explain it later. Now I want to do this. We have the third example. We know what's the fifth of the sequence is 2. The 7 of the sequence is 4. This is our formula. But we want to know what's the first term. We want to know what's the ratio also. So how do we do it if we don't know what's the first term? And also we don't have the equation, like in terms of what? Because if we would have the term in terms of what we're doing it, this would be so easy because you only plug one, as we will see later, and this will come beautiful. So we can do this. We can cheat. We have the fifth, so we put this fifth minus one will be four. So all of this is equals to two. As we see here, when we did the seven, we didn't know what was the answer. Okay? But in this case, we know what's the answer. So the a sub n get replaced by the answer that it's two. So two it's equals to the a, the first term, times to the power of four. And the seventh term, we put the seven into the one, we get six. So the ace the number of that term it's four. Now we can do this. We can divide these two terms of sequences. We so as you can see, this first term we simplify, we get rid of the r square, the ratios will be having as a square because we this is another thing in that if we divide two exponents in logarithms, I'm sorry, I was that was the word. If we have a division in logarithm, we just simply subtracting. So this is equals to 4, this is equals to 2. So this 4 over 2, it's plus or minus the the square root of 2. Now, I don't want this video to be too long, but whenever you're doing a square root, you will always have to get two answers. Obviously, in this case, this square root gets into this fraction in which you can simplify it by giving it by the both. So we get rid of this 2 because it's 1, and we get rid of the 4, which is 2. So we have a positive square root and a negative square root. This is a lot of work, but we need to confirm, we need to see if any of those two can be an answer, because when we do the square, we're really saying, okay, in this function there is one, because there's a lot of things we can discuss here with the square. Now, the ratio means that in these lines gets divided, one goes the other way and goes the other way, but we have to see which one of those is the real ratio, you know? And in this case, as we look at it, so as we know, we will take in the fifth term in the sequence. So we will do the same thing, because now that we know the ratio, we just substitute the r to the 4 as we look at here. 2. Now we're trying to solve for the first term in the sequence. This is really important if you really know in what terms are you using the sequencing. Okay, if you don't know the terms of the series, so you multiply by this. You can do it in two ways. Put this 4 uh, right there into the 2, or put this 2 into 4 divided by 2, in which you get 2. So 2 in 2 is 4. I hope you get this. So we'll do the same thing. We divide it 2 over 4. We can simplify it 1/2. So the first term in the sequence is 1/2. If we do the other side, this is the same, because if we multiply a negative number and that number is not odd, that number converts into positive, as explained before. So I'm not gonna say it anymore. I hope you understand, because I say it a lot of times. Let's continue. Partial sums of the geometric sequence. We are halfway, guys. Okay. Partial sum of a geometric sequence. The following discussion illustrates the method for finding the formula for the sum of the first n terms of a geometric sequence. Such a sum is called partial sum of the sequence. The sum of the first 6 terms of the geometric sequence can be indicated as, so this is a little example of how this will look. Some professors would rather put the 6 like on top of the symbol notation, like in front, on top of it, like in the way of exponents. But some others would prefer to put it on top, really, of the symbol notation, and the k on the bottom. To find the value of this partial sum, we write the terms, simply add them. So we want to do this example. We want to add all of these numbers and do it, okay? In terms of in terms of 1 divided by 3 to the power of k. So remember that the k, we have to substitute the k till we get the 6. As we look here, we're adding. So in this case, we have, now if you're asking why this 3 to the power of 6 is on the bottom, what's going on? Remember that all of these threes, this is my pointer. As you can see, my pointer, I'm pointing to the first term of the sequence. All of the numbers below has to have the same denominator. So I had to multiply this number to the 6. Well, I had to add 5 powers and then move it on to the top. So that's why we have 3 to the 5th, 3 to the 4, 3 to the 3, because we only need 3, 2, we only need 1, and this is really just simplifying that we have 1, because we have in terms of 3, 6. So now we can do it with a calculator. I don't want to do the whole thing, but 3 to the 6 is this number, and the other number is this number. And so this is the total sum of this summation. So let's start. Let's do this. Let's build a formula in this way to actually find a summation of everything. This will be really similar to the last one, uh, the arithmetic. Adding a few terms is relatively easy. However, the following procedure will help in understanding the development of general formula for partial sums. Write the terms in order and then multiply each term by one third, the common ratio. Arranging the terms in a vertical format, then subtracting gives the following results. I'm gonna go really easy and fast with this. We have the summation. So let's take this example. Let's build the formula. So as previously said, we have all of this. Now here we want to divide it by one third times s. What we want to do here is do the same thing as with the arithmetic sequences, in which we take the first term of the first of the sequences, and we take the last term of the sequences, and we add them. We take the second term and the second to the last, and we add it and we add them too. So that's what I'm doing here. I have one third and one third to the sixth. This will be one to the seventh. One third to the second, and so on. So right here we have the summations but backwards, in this way we one third to the sixth added to the one third. Okay, now because we have to subtract everything as Gauss did, we have to subtract it. So we will have this six, as we said. The only numbers that we will end up having is the first term and the last term. And we also want, so right here, what I did was to grouping these numbers. I'll group this number because I want to get rid of the s, because we have two. So I want to get rid of that too. So as you can see, now where this s came from? This s came from to the first, the one here on the first. So s minus 1 to the divided by 3 times s. So this will be equals to 1 minus 1 divided by 3 times s. As you can see, we have the same, because 1 times s is s. In negative 1 divided by 3 times s is this. So we haven't touched anything. We have the one third of the remainings of the subtraction is the first term and the last term. First term and last term. Okay. So then what I did here is divide this s. So now we have just one summation. the first term minus the last term minus 1 minus the first term. As you see here, this is equals to the 7. I just rewrote it to the 7 power and this and this. Now let's do it with the an, with with just the numbers, with just the letter that doesn't mean any number, but what I want you to know, it's process. So we have the first term. Let's recap a little bit. The second term is equals to the first term times r. Okay, the third term in the sequence is the first term times r squared. All good. Why it's r squared? I explain it. Because a sub 3 is equals to a sub r. And a sub 3 is equals to, we still have one r. So what I did is just adding the r because we're going up. As we're going up in the equation that we are reviewing, I didn't create it. It's an online. Gauss did it. We are adding the exponents in the ratio. Okay. So if we take any number, like kind of like the number behind that number, will be equal to the first term times r n minus 2. This is just a review. So the first term is equals to the first. So any term is equals to the first term times r n minus 1. There's nothing new. This is just a recap. Now let's take the s and let's put all of those numbers there. Now let's take those numbers, flip it, and let's start adding them. But in this case, subtracting. I'm sorry. In the arithmetic sequence, we're adding, but in the geometric sequences, we're subtracting. So if the first term times r to the power n minus 1, we took this number, we put it here. This number, we put it here. The second to last, we put it to the second. And the second, we put it to the second to last. I hope I'm under you're getting what I'm going through. I hope you're listening to me and kind of understanding what I'm saying. But in small words, all of those numbers cancel because if we think about it in the arithmetic sequence, yes, we only need the first and the last one as this one because we are adding two times the same sequence. So we have s minus rs. The only numbers that the remainings is the first term and the last term. This is just the same as this one. We group, we divide, and we get this. The first term, it's equals to 1 minus r. Now I want to explain you what happened here. So we have the first term and the last term. how this number was converted to the first term number. And the number on the bottom of the division comes from dividing the multiplication. But here we notice that minus a1 minus the first term times r to the power of n can be wrote in this way. This is where it came. Okay? A1 times 1 minus r to the power of n in parentheses. So all of this gets transformed to this. I took the first one. This is very important and it's very and it uses a lot in calculus. This is another way of thinking and it's really cool because you really get to know kind of like you think different, like you can, okay, this can be read in this way. We're doing the same thing here. This, the first term, gets multiplied by 1 minus the r to the power of n. All of this is equal to this. This should be alright because if we multiply this, the first term, by 1, we get the first term. If we multiply the first term by the r, we get this one. And because it's negative, this will be all equal. So we don't have any problems there. This one in the bottom came from the division of multiplication. So this cannot fail. The end partial of the sum of the first term of the geometric sequence is where the radius is, we have it here. So the first term in the sequence is this one. You see what happened here? We took how to get the ratio and how to transform it into any terms of the sequence to get the ratio. We did the same thing to add all the numbers. But when the ratio cannot be 1, because if the ratio is 1, then this might not work because we're saying, well, it works, but we can do it mentally then because then we're saying we don't have the ratio, we don't know if this. Let's do an example so that we can see. I'm burning, my head is burning right now, and I did examples. This should be really easy. It's kind of hard. It's it's just the process that it takes too long to get to the real answer. But if you look at it, it's a really good way because instead of adding one in the second number and the third number, you can really just this one and add all of the numbers. So I think it's a really good time to just do this instead of doing all of this, you know. The formula works, but it could get a little tricky. Okay, let's do let's do this example. The partial sum of a geometric sequences, the summation of the first term to the 10th term in terms of 1 divided by 2k. I wanted to do this the less. I don't want this video to get too long, but just taking too much. We're almost done, so don't worry. We must find the R. We need to find the ratio. But we know how to get the ratio, right? Because we know the a sub k and we know a sub k plus 1. So to get the ratio, we just get a higher number in terms of this, in terms in terms of the sequence on the equation of the sequence. The only thing that we do here is this k gets added 1, and the lower it just gets k. So we just flip it. We have 1, we have 2 because this 2 gets to the power 1. 2k, we subtract this 2k, so we got 1 over half. That's the ratio. So the first term is 1/2. Why? Because this k, as I said before, we just put 1 here, and we had the first term, and we have also the ratio, which is the same. Look. So now, now here, it's where it gets a little hard, but don't worry. We have, so we just write this in this way. Wait, guys. We have to write it in this formula. Wait, in this formula. Look. So now that we know the ratio, we can just write it in this way because we developed the formula and we prove it that it's right. Okay. So this it's 1/2. I'm gonna explain you why. Because we're saying that this is the first term, right? Has to be the first term here times this number, which is 1 minus the ratio. The ratio is 1/2 also to the number. Now, what's the number that we want to know? This number n gets substituted by the limit. Why? Because we're using the formula of adding all of the numbers. Okay? We will look at more in the future right now that if we can just find, we want to find a specific and in a specific number, we can just put that number, like that point in the term. If we want to look the 7, what's the number? What's the number of the 7th term of the sequence? We put the 7. But in this term, we want to add the 10. Okay? We will do the same, and we will take the 6 and we just subtract it and we'll get that number specifically. Or you can just put the 6, whatever you want to do it. So we get 5. 1 minus 1/2, I'm sorry. This 1/2, it's also because the radius, but without the exponent. So we have the first term, the last term in the formula times the first term. So we have, look at this. We're dividing 1/2 right here. So we're dividing 1/2, 1/2. 1 minus. So this 10 gets distributed in the division. It is 2020, 1024. It's the final. Now this 1024, this gets converted to 1. Now I'm gonna explain you what happened here. What's going on? This number on the bottom gets canceled because this number, the one in front of it, it's a bigger number. As I said previously, if the first number it's bigger, you're subtracting a less number, you will get a positive number, right? But if you're subtracting a negative number minus a negative number, you will get a larger number, but negative though. So this 1 minus 1/2 is 1/2. This 1/2 gets divided by 1/2, 1/2. We get rid of the division. Now we just uh, focus on this one right here. As explained before, this 1 minus 1 over 1024, we have to have the same denominator. So we multiply 1024 on the bottom and up. So 124 minus 1, this 124 is a bigger number, so it will be a negative, it will be a bigger number. This would be equals kind of like 0.9. So the total number of decimation will be kind of like 1. Small. Yeah, so small number. Let's do another example. Now you may hate me right now, but there are some special operations in which you multiply two numbers. So the summation of the first term to the fifth in terms of -1 to the power of k times 3 to the power of k divided by 2. Now this k divided by 2 can be said as it's a square root of 3 to the power of k, but we can write it this way. This is very helpful in calculus. So this is one step into calculus. It's kind of like a review. In Before going to calculus, this is really helpful because you have to know everything of this. I'm talking to those who are still in school, in high school, who's taking trigonometry or pre-calculus. So we we have the a sub k plus 1 divided by a sub k. We still have to do this one because we don't know what's the ratio, and we want to know what's the whole summation of the in terms of this formula. So the only thing that we do here is just add 1, so it will be -1 k plus 1. We also do the same here, k plus 1 divided by 2. And on the bottom, we just copy the same thing here. I wrote it in this way, as you can see. Now, now we have to simplify this thing. Negative 1 to the power of 1. As explained before, we're breaking down the exponents into multiplication, but it's really the same thing. So negative 1k, this negative 1 came because it's been multiplied by 1 to the power of 1. We do the same thing here. 3k divided by 2. And 3, 1 half. I hope you can see this. This plus means that we have this is two different things. You cannot combine them. So you have to take both of them apart with the divided two. Okay. We want to know what's the ratio. So okay, so let's simplify. We have this, we have this. Now we have on the bottom we have 1. But what I did, yeah, we have 1. So we have negative 1 times 3k divided by 2. Now what I did here is convert because we want to get rid of the we want to know what's the ratio. So this negative 1 will be negative 3. So to the square of negative 3 to the power of k. But to the power of k really doesn't matter because we just simplify the whole thing into r. Okay. So the radius is negative 3. And if we go back and we plug 1 here, 1, negative 1, 1, we look and we have the same thing. 1, so it will be negative 3. See it, this one as a 1, negative 3. So this negative can be written in this way at the end or at the front. It's really important because there are some other things when we are grouping imaginary numbers and real numbers, and sometimes you can get real confused. So a lot of people like to put it on the here, but we're not talking about imaginary numbers now. So we had this square root of 3 to the power of 5x. So now that we know the ratio in the first term, we wrote it in this form. The first term is negative 3. 1 minus the ratio to the power of 5, which is the limit, and 1 minus the square root of 3. And right here we can write it as 1 plus the square root of 3. The square root of 3. Now, the correct way of solving this is by this 5 gets into the 3. Forget about the 1 for the moment. And we know that's negative, but it has to be multiplied by a negative. So we will convert as a 1. So 3 to the fifth powers is 81. No, I'm sorry, it's 253. Now 253 can be broken down into 81 times 3. We wanna so the square root of 81 is 9, but we have this 3. So we take this This 9, we put it as the square root of 3. And this 1 plus 9 cannot be added because those are different things. And we can just simply leave it like this.